variations on the binomial random variable, and we will generalize it to the multinomial random variable. Okay, so let's do a review problem first, and then we'll go on to the negative binomial random variable. Okay, so we have a machine which produces widgets. 80% of the time you have a success, the widget works. 20% of the time you have a failure, the widget is defective. And the this process is independent, right? So one trial after the other, you get your widgets. The success or failure for a previous widget doesn't influence the success or failure of a current widget. Okay. We're asked, what's the probability of getting 5 working widgets from 7 produced? So think of it this way. What's the probability of getting 5 working widgets and then 2 failures in a row? So 5 successes and 2 failures in a row. What's that exact probability? Successes and probability of successes and failures are independent. So, right? So it would be the probability of success 5 times the probability of a failure 2 times because of independence. Now, if we don't care about when the successes and failures occur, how we arrange our symbols S and F in a row, right? We can have rearrangements, but we have the same probability. So there are 7 trials, and we have to select 5 of them to be successes. All right? So that's the total probability of getting 5 working widgets from 7 produced, and that's just the binomial random variable that we were talking about previously. Okay, and in our case, P was 0.8 and Q was 0.2. All right, now, okay, as I said, that was the binomial random variable that we were talking about in the previous session. Now let's change the question just a little bit. What's the probability of the 5th work? There are going to be 5 total successes. We're saying, what's the probability of exactly 5 successes in 7 failures, with the added restriction that the 5th success, the final success, occurs on the 7th attempt. Okay, so we've got 1, 2, 3, 4, 5, 6, 7 attempts, right? And we specify that there's to be the 5th success should occur on the 7th attempt, right? Now how do we work out the probability? Okay, so in the remaining 6 attempts, right? So we need 4 successes in 6 trials. We need 4 successes in 6 trials. So we can think of this as being the problem of finding 4 successes in 6 attempts. They can be arranged in any way, followed by getting a success. Okay? So now what would the probability be? Right. You would have to have this. Okay. So previously you had 7 choose 5 ways of arranging 5 S's in 7 slots and 2 F's. Okay? But now the last one you know is going to be an S. So you have to arrange 4 successes in 6 attempts. And then the last one is supposed to be a success. Okay? Now, what's the probability of getting 4 successes in 6 attempts, followed by the probability of getting a success? Well, you have to have p to the 4, right? This part here takes care of the probability of what's going to happen in the first 6 attempts. And then it's followed by a success. The probability of a success is a p. So that's the probability of getting a sequence with all the restrictions that we've given. Okay? But then I may as well, I'll bring the p in here. P to the 5. Okay? So this is a different random variable, right? The probability that we're getting looks a lot like the one for it looks a lot like the PMF would have been for the binomial random variable, but it's a little bit different because we're insisting that the final 5th success should occur on the 7th attempt. Okay? Okay, so we discussed all of that. Again, in our example, we're taking p to be 0.8 and q to be 0.2. Okay, now so this is what we have. And so now, using the terminology that we had last time, we have n independent Bernoulli attempts in a row. The probability of a success is a p. Probability of failure is q to the 1 minus p. And now let's say that I want a total of 5 successes, and the 5th success should occur on the nth trial. Then what would we have? Okay, so this is what the sequence looks like. There are n minus 1 trials, and then there's the nth trial. And we have the 5th success should occur on the nth trial, right? So that means I need, over here, I need 4 successes and all the failures, 2 failures, should be arranged among, in any way. Yeah. So, right, sorry, there would be so the number of, there's going to be 5 successes. So there's going to be n minus 5. There are going to be n minus 5 failures. Okay, all the failures have to occur in here. So there's going to be n minus 5 failures. If 4 successes arranged anywhere in n minus 1 trials, and the fifth success coming in the nth trial. Okay, once again, independent results, and the probability of failure and success are not changing from trial to trial. Okay, so now what's the probability of such a result happening? All right. All right. Okay. Okay. So okay, so let me just so 4s in n minus 1 trials and s in the nth trial and n minus 5 f's in n minus 1 trials. Okay, so for this part here, the probability is what? The probability is from n minus 1 trials, you have to choose 5 minus 1 successes. Okay, and so you have the probability of a success, well, 5 minus 1 times, and the probability of a failure, n minus 5 times, and then that takes care of all, from there to there, n minus 1 trials, and then you have the last trial, which has the probability of a success with probability p. And I can combine the p and the over there and here. So that's the probability that I have. Okay. Now let's try it again. Generalize again. Okay. Nothing special about 5. Let's generalize that 5 to a k. So n Bernoulli trials k successes the kth success, the last success, is on the nth trial. Okay, so then what do you have? All right. N minus 1, choose k minus 1. Right? N minus 1, choose k minus 1s of distributing k minus 1 s's in n minus 1 slots, right? So then p to the k, q to the n minus k. Yeah, this will be k minus 1, but then that's for k minus 1 and then another p. Okay, so that goes in there. Okay, so a slightly different binomial random variable because we have, well, we've changed the problem slightly. We've added another condition. And by doing that, we've reduced the number of possible arrangements. Okay? So then we get this, right, which we have over here. Okay, and this is giving you the values that the PMF takes for the, We call this the negative binomial random variable. Okay. Okay. Yeah.
Why is it called that? Is it negative allowed?
I think just because we're subtracting the 1 off or something. Okay. So once again, you have the same condition. You have Bernoulli trials again, right? So you have the same conditions as you had for the binomial random variable, right? So you've got independent Bernoulli trials. Probability of success, probability of failure do not change from trial to trial. Okay? And we're saying, when does the kth success occur? Okay. And this is how you would write the PMF. Okay. So the expectation for the negative binomial random variable, if you let x be the trial on which the kth success occurs, right? That's right. So you do your experiment repeatedly. You're doing the same thing over and over again until you get your kth success. Okay. Then the expectation is given by kq over p. The expectation of the, okay? And the variance is kq over p squared. Okay, once again, you can do these by, go back to the definition of expectation and variance. Okay. Yeah.
The previous one, it was NP and NP.
Yeah, yeah.
That was also.
And, okay. Now, previously we've discussed the binomial random variable. This is slightly different. So now we expect then that the expectation and the variance might also be a little bit different. Okay. Okay. All right, let's skip the exercise. Okay. Again, I might have a question which is it's related, same sort of setup as you have for the binomial random variable. The question we're asking is slightly different with the geometric random variable. And that is, I want to know what's the probability that I need k trials, so a certain number of trials, to get my first success. I might have something that only occurs rarely, or isn't guaranteed. I want to keep going until I have a success. Okay? So I want to, let's say I'm manufacturing some sort of a device. And quite often the device does not work properly on the first attempt. I need one of them for my lab. So I need to buy the materials and book the time and so on and so forth to produce some sort of a device. And I know that success only occurs 20% of the time that I attempt to build this device. So I want to have an idea of how much material I have to order, how much time I have to book in order to have a reasonable chance of actually producing the device, a functioning device. Okay, so that's what we would use something like the negative binomial for. Okay, so let's suppose I've got a biologist. They have to induce a disease in a rat. And this, you do it with an injection. And the injection induces the disease 80% of the time. Okay? So what's the probability of getting a diseased rat in the first attempt? 80%? That's what we just said, right? Okay. Okay. What's the probability that it would take 2 attempts? Right? Right? So what you're saying is, what's the probability of getting a failure followed by a success? Well, the probability of failure, Q, times the probability of success, P. So 0.2 times 0.8. Okay? So 0.2 times 0.8. Okay. What's the probability it's going to take 10 attempts? Yeah. So I need the sequence failure, 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 9 times failures, followed by success. They're independent, so I can just multiply the probabilities. Right? So q to the 9 times p. 0.2 to the 9 times p equals 0.8. Okay? Okay, so if we're writing p as the probability of success and q as the probability of failure, q to the 9 times p. Okay. How about what's the probability of x attempts? Right? So let capital X be the random variable. How many attempts does it take to induce the disease? Small x is one of the values that capital X can take. So what's the probability of x attempts? Right, right. So you need to fail x minus 1 times, followed by a success. So q to the x minus 1 times p. Okay, so that's what we're saying there. Okay. So basically what we've done is we've derived what's called the geometric distribution. Because that kind of reminds you of the geometric series, I guess. Okay. So the probability that it would take small x attempts to generate the first failure, the first success, followed by x minus 1 failures, is p q to the x minus 1, where q is equal to 1 minus p. Okay. Okay. So the expectation for this geometric random variable is 1 over p. So if your probability of success is 1%, then you expect to do 100 trials before you get the first. Right? And the variance is 1 over p squared, which means the standard deviation is what? 1 over p. Right? Right? So if you, let's say it was 1% chance of inducing the disease in the rat, how many rats do you want to order for your experiment? Maybe 4 would work, right? Because you expect 400, right? So you expect for 100, that's the expected value. But you want to have more than the expected value, right? How much more? Let's say 3 standard deviations more, right? So then you're well covered. You know, there's a better than 90% chance that you will get your first success in, say, 400 trials. All right. Now, so far, okay, we go on to the multinomial random variable. So far, we've been supposing success or failure, or two outcomes, yes and no, on or off, success or failure, black or white, right? But we could imagine repeatedly doing something, and there could be more than one outcome. So if I roll a fair die, or even an unfair die, right? Standard six-sided die, there are 6 outcomes. And I could imagine rolling that die over and over again, right? And the probability of each of the possible outcomes, let's say, is constant, and they're independent. Results are independent. So it's kind of like the binomial random variable, except it's generalized in the sense, or perhaps it would be something like the binomial random variable, but generalized to take into account that there is more than 2 possible outcomes. Okay? Yes?
Are we going to have like a formula sheet or something? Or like example?
Yes, we'll have some sort of a sheet, yeah. Okay. So once again, I can imagine doing repeated trials like you had for the binomial random variable, but I imagine that I have more than 1 possible outcomes. I could have 6 possible outcomes, like you have for, like you have when you roll a die repeatedly. So it'll turn out that the binomial random variable will be a special case of what we're going to do here, the multinomial random variable. Okay, so once again, we'll build this up slowly, taking a specific example and then generalizing it. Okay, so I'm going to roll one die 5 times. Die is fair, 6-sided die. What's the probability of getting exactly the sequence 3, 4, 2, 2, 1?
6 choose 1 to the power of.
No, that's exactly that sequence. Okay? All right, so it's the probability of a 3, rolling a 3, times the probability of rolling a 4, times the probability of rolling a 2, times the probability of rolling a 2, times the probability of rolling a 1. Okay, well, rolls of a die are independent. Right, okay, so you're right. This is, okay, so let E1 comma 3 be the event of rolling a 3 on the first roll. E2, 4 is the probability of rolling a 4 on the second roll. E3, 2 is the probability of rolling a 2 on the third roll, and so on. So this is how you get that sequence. You get exactly that event. Okay? Now, rolls of a die are independent of each other. Right? So I can just multiply, because of independence, I can multiply these probabilities. Okay. Now, the probability of rolling a 3 is not changing from roll to roll. So let me just call that P3. It's the same whichever roll it is. And the probability of rolling a 4 doesn't change from roll to roll, so let's just call that constant P4. Times the probability of rolling a 3. Times the probability of rolling a 2, times the probability of rolling a 2, times the probability of rolling a 1. That okay? All right, and okay, now all of those probabilities are 1/6 if it's a fair die. So we could have just written 1/6 to the 5th. But at some point, I want to allow for the possibility that the different outcomes have different, they're constant from roll to roll. The probability of a particular outcome is constant from trial to trial. But not all of the outcomes, perhaps, we want to have the same probability for them, right? So we can write this like this, right? But right now, if we're assuming fairness, nobody's cheating, then all of those probabilities, all of these probabilities would be 1/6. Okay. Now, this was for a particular roll. This was for a particular sequence, right? This sequence, I was going to get the sequence 3, 4, 2, 2, 1. Particular sequence. What if I said, what's the probability of, if I reorder that sequence, the probability doesn't change, right? Because I can just rearrange these, right? They're not changing from roll to roll, so I can say that this is the 5th, this is the probability of rolling a 3 on the 5th one or something like that. But that's the same as the probability of rolling a 3 on the first roll, right? So the probability of all of the rearrangement, all the sequences which come from rearranging that sequence, the probabilities are all the same. So if and these are disjoint events. Rolling a particular sequence is disjoint from rolling a permutation of that sequence, which is not the same. Okay? So if I want the probability of all the sequences that have 1, 3, 1, 4, 2, 2s, and 1, 1, then what's that probability? Right? We have to count up how many rearrangements are there and then multiply it by this same probability. Okay, right. Right. So now we have to multiply by the number of arrangements like we had before. Before we just had n choose k. Right? Now it's going to be slightly different because you have more than 2 outcomes, right? So you've got 5 symbols. If these were 5 distinct symbols, then there would be 5 factorial rearrangements. Okay, so the 3 is a single. 2 of the symbols are the same. So the rearrangements of those 2 symbols, because they're the same, are not a new sequence. So in this 5 factorial, I have an overcounting by 2 factorial. Okay, so the 3 is appearing only once, right? So there's no overcounting involved there. So for the 3, I can just divide by 1. Okay? Dividing by 1 doesn't change anything, right? And the 4 only appears once, so I'm just going to divide by 1. Do that. And the 2 appears twice, so I divide by 2 factorial, because otherwise there's an overcounting in this factor. And the 1 appears only once. Okay? So that's the probability of that sequence and all of the other rearrangements of that sequence occurring. Is that okay? All right. Now, okay, that was discussed. Okay, and if the dice is loaded, as I said, you should write it like this. This is what we have here. And here's the probability of what we, okay. And if we wanted to match up these with these factors here, we would write that as P3 to the 1, P4 to the 1. Now P2 is done twice, and P1 is done once. Okay, so that's one way of writing it. Okay, it's convenient to write it this way as we generalize. You'll see from step to step how we're moving towards the most general formula. Okay. Now, yeah.
For multiplication probabilities, just the probability, it is not necessary that the probability is the same because we're writing it out.
No, now we're allowing the probabilities to be, right? Not necessarily the same. Okay, so now, let's say we have a loaded die, right? What's the probability of rolling n1 1s, n2 2s, n3 3s, n4 4s, n5 5s, and n6 6s? All right, so and n1 plus, so let's say 3 1s, 2 2s, like, and the other zeros maybe, you know. Yeah.
1 by 6 power n.
Okay, so if we roll, if we have let's just think of the exact sequence where first we roll all the 1s, then we roll all the 2s, and so on, okay? So we're going to roll n1 1s. Exactly. What's the probability of rolling n1 1s exactly? Okay. The probability of rolling a 1, it's a loaded die perhaps, so maybe not 1/6 anymore. It means that it's not fair. Something can have a value, one probability could be bigger than a 6, another probability could be less than a 6 for that result. Okay? So if I roll, the probability of rolling a 1 n1 times in a row is how much? It's p1 to the n1. Okay? What's the probability of rolling a 2 n2 times? After rolling n1 1s, you roll n2 2s. All right. Well, you would then multiply this by p2 to the n2. Right? And now you roll a 3 n3 times. And we can just multiply these because the results, the rolls are independent of each other. Okay? Probability of A intersection B is probability of A times the probability of B when events A and B are independent, right? So we're assuming independence here. So we rolled a 1 n1 times, followed by rolling a 2 n2 times, followed by rolling a 3 n3 times, followed by rolling a 4 n4 times, followed by rolling a 5 n5 times, followed by rolling a 6 n6 times. So that's the probability of that sequence. All the rolling all 1s, then rolling all 2s in a row, then all 3s, then all 4s, all 5s, all 6s. Okay. What's the probability of any rearrangement of that sequence? Right. So if we imagine the probabilities of all of those, that's one possible outcome. Or we can think of it as one possible event. We can consider rolling a rearrangement of those 1s, 2, 3, 4, 5, 6s as another event. Because they're distinct, we can add up the probabilities for that. So if we work out how many rearrangements are there of these results, then multiply them by this probability. So that'll be the probability of getting n1 1s, n2 2s, n3 3s, n4 4s, n5 5s, and n6 6s in any order, right? So now let's say, okay, so we're in this particular case, we're saying there are 12 rolls. Okay? So that means in particular that these exponents here, n1, n2, n3, n4, n5, n6, they have to add up to 12. Right? Okay. So there were 12 rolls. Let's say that there were 12 distinct outcomes. If we have 12 different letters or something like that, right? How many ways are there of arranging 12 different symbols in a row? 12 factorial. Okay? Now, were they all distinct? No, they weren't. N one of those symbols were all the same. They were all 1s. Right? So an n1 factorial, there's an overcounting by n1 factorial in this 12 factorial. So we have to divide through by that to take care of the overcounting. There were n2 2s. So those 2s were not distinct. And here, if I just write 12 factorial, I'm pretending that they were distinct. But if I rearrange the 2s, if I interchange the 2s with each other, n2 factorial ways, I get nothing new. There's no new arrangement. So here there's an overcounting of n2 factorial in there. And similarly, n3 factorial, n4 factorial, n5 factorial, and 6 factorial. Okay? Is that all right so far? Okay. Okay, so that's this discussion of the factor out front. So if you have 12 trials with 6 possible outcomes, P1 is the probability of getting the first outcome in each trial. P2 is the probability of getting the second outcome in each trial. Up to P6 is the probability of getting the sixth outcome in each trial. And then N1 is the number of times that the first outcome actually occurred in those trials. N2 is the number of times that the second outcome occurred in those 12 trials, and so on. Then this is the probability of getting the first outcome n1 times, the second outcome n2 times, and so on. Okay? So what's the last thing left to do? Generalize this 12 to some n or k or something, right? So we're going to roll the die capital N times. Then what's the probability? Okay, so you get this factorial, n factorial, capital N factorial instead of 12 factorial as we generalize. Okay? So if you roll the die capital N times, and you're looking for the probability that the first outcome appears n1 times, the second outcome appears n2 times, the kth outcome appears nk times, where all of the small ni's add up to capital N, right? pk is the probability of the kth outcome occurring on a particular trial. Then this is the probability that you have. Okay? One more generalization left to do. What's that? Well, we're assuming 6 outcomes here. There can be more than 6, right? Right. So let's say it's k outcomes. Okay? So you've got the ith outcome has a probability p sub I occurring on any trial. We're interested in it appearing ni times, where I goes from 1, 2, 3 up to k. And these exponents here all have to add up to capital N, because there's capital N trials. Okay? So this is a probability of, in capital N trials, with k possible outcomes in each trial, and pi being the probability of the ith outcome, this is a probability of the ith outcome appearing ni times in the total capital N trials. Okay? The binomial random variable that we did in the previous session is a special example of this, of only 2 possible outcomes. Okay? Okay. So this factor that we have out in front of the probability, which is counting the number of sequences, right? Sometimes people write it like this for the multinomial. It's called the multinomial coefficient. People write it like that. I prefer to write it like this because then I can see what that term means easier, I think. But you might see this in your textbook, so you should know it. Okay? So, once again, so the probability that you get this many occurrences of each of the k possible outcomes, given that these are the probabilities of each of those outcomes occurring, these are constants, over n trials, is this factor. And remember that the sum of the occurrences of each of the possible outcomes has to add up to the total number of trials. And the PIs have to sum up to 1. Okay? Okay. So now we're counting the number of we're counting the number of possible occurrences. In the binomial random variable, we were counting the number of successes, right? But if there are 3 possible outcomes, then I will be counting the number of times that the first possible outcome occurs, the number of times that the second possible outcome occurs, the number of times that the third possible outcome occurs. So xi, capital Xi, the random variable here, is the probability that the number of times in n total trials that the ith outcome occurred. Okay? And its expectation is somewhat is the number of trials times the probability that the ith outcome occurs on any one trial. So that's the expected number of times that you expect to see the ith outcome in n trials. Is that okay? Okay? What's that? Okay, so with the binomial random variable, you had the expected number of outcomes. Was n times p. The number of trials times the probability of a success. Now, if you consider success and failure as 2 different outcomes, right? So we would say the number of the first outcome, the success, the expected number of successes, or the number of times that the first outcome would occur, is n times the probability of the first outcome, right? Now, the second outcome in the binomial random variable was, what was it? It'd be n times q, the probability of failure. But I could call that q p2 to mean failure is the second possible outcome. Okay? Now, if I have 1, 2, 3, 4, 5, up to 37 possible outcomes, right? Then the expected number of times that I see the first outcome will be n the number of trials times the probability of the first outcome. The number of times that I expect to see the ith possible outcome is the number of trials times the probability of the ith possible outcome occurring. Okay? And the variance, remember before the variance was npq for the binomial random variable. So this generalizes as the variance of the number of times that you will see the ith possible outcome occurring in n trials is n times the probability of the ith outcome occurring times the probability of the ith outcome not occurring on any one trial. Okay, so those were variations on the theme where you have repeated trials and you don't have any, the probability of the outcomes is not changing from trial to trial, and the results are independent. Okay? All right, any questions? Okay, so next time there isn't a lecture, right? There's a test instead, right?